Hi, everyone. It's a great pleasure to be here physically, of course. This is one of the few talks that I could give in presence, so I'm very happy for that. And so in this talk, I will present some of the work that we are doing now in Milano Bicocca about the massive black hole binary path to coalescence. All this work is done by myself and in collaboration with all these people here, especially Elisa Bortolas and Alessia Franchini, that are other two postdocs in Milan. So, massive black holes. As you may know, if we observe the nuclei of several galaxies, we can observe compact objects that generally produce a quite intense electromagnetic radiation in the center of galaxies. And the source of this radiation seems to be this very compact object that we call massive black hole. They are black holes that they are very massive, so with mass in the range from 10 to the 6 up to 10 to the 10 solar masses. We also know that from the cosmological model, the largest scale structure of the universe is dominated by the dark matter, and the growth of this structure proceeds in a hierarchical way. So during the cosmic history, less massive halos of dark matter merge to form more massive ones. Galaxies that form in these dark matter halos can therefore undergo merger events. And so if every galaxy hosts at least one massive black hole, then we can form binaries of massive black hole within the same galaxy. And so the next question is, which can be the evolution of these massive black hole binaries? And maybe we can think about their possible coalescence because of the emission of gravitational waves. However, as you may know, things are not so simple because two black holes inside a real galaxy are really tiny objects. And in fact, they have to cover something like 10 order of magnitude in separation from the kiloparsec scale down to the massive black hole binary coalescence. Historically, this long journey has been characterized by three different evolutionary phases. So first, large scale evolution, in which usually dynamical friction is considered the main actor. So in this stage, the two black holes do not see each other, but they are dominated by the galactic background. And they sink towards the center of the galaxy because of dynamical friction. At some point, if everything goes well, a bound binary can form in the central region of the galaxy, and then other processes can further shrink this binary. And again, if everything goes well, we can reach the final phase of this evolution, in which the dynamics is dominated by the efficient emission of gravitational waves, and the binary can merge. This phase will be very important because will be the phase that could be actually observed through gravitational waves, and in particular by these two kinds of detectors: LISA, laser interferometer space antenna, and PTA, pulsar timing array experiment. So during the past year, several people, several scientists addressed this long journey, and they found that the situation is a bit more complicated, and other several processes have been highlighted to influence this long journey. And to study these processes in very detail, we need different approaches and techniques. And so here we find one of our long-standing dilemma in astrophysics. So we need to balance a fully numerical approach that is much more accurate in investigating the process under study, or semi-analytical approach that are much faster but relies on several approximations. And to extract at most the scientific results from our study, we need to balance these two aspects of our research. Sorry? Yes, this is the separation. So from kiloparsec scale, so the galaxy scale, down to the black hole event horizon. So sorry, it's on the opposite direction where you usually think about. Yeah. Of course, yes, feel free to ask questions, no problem. So I can start from the larger scale evolution. So we have galaxy mergers, and then we have two black holes inside a new galaxy that has been formed. So here, usually, dynamical friction has been considered the main actor driving the evolution. Dynamical friction can be think about as the drag force arising from the cumulative effect of a large number of hyperbolic encounters between the massive black hole that is moving within the galaxy and the single stars that are in your galaxy. This is, of course, a local description of the dynamical friction that dates back to the great work of Chandrasekhar. It has been found that dynamical friction is a much more complicated process that involves the whole galaxy, so the global response of the galaxy because of the merger of the motion of a massive perturber within the galaxy. And probably Thomas will be happy to explain a bit more about that. So address the most difficult question to him. But here we see that also the local approximation of dynamical friction is a very good description of what happened in realistic galaxies. Nevertheless, so the process is quite complicated to tackle analytically, and in fact, you can analyze it analytically only in very idealized systems, for example, usually in spherical symmetric systems. But as you know, galaxies are much more complicated than that. So they can show different range of morphologies, not smoothness, and a certain degree of rotation. So to properly simulate dynamical friction in realistic galaxies, you have to run full embodied simulation or even cosmological simulations. But as you may know, you cannot run millions of them because they are very computationally expensive. So we have to find a way out. And in fact, during the past year, we decided to go to the semi-analytical way. So the semi-analytical approach has the great advantage that we can simulate a galaxy through the introduction of several smooth profiles. They can be of any number, since the Poisson equation is linear. And they can be of any shape. They can be spherically symmetric, so you can simulate the halo or the bulge. They can be axisymmetric, you can have disk, but they can also be triaxial. So you have a global gravitational potential that can be formed by multi-components. And you consider massive black hole as test particles. So you integrate numerically the orbit. But since now the equation of motion are ordinary differential equation, they are quite easy to integrate numerically. Of course, we have the disadvantage that we are considering test particles. So there is no back reaction on the galaxy. And so we have to introduce the effect of dynamical friction through some dissipative forces like this one here. This is a very simple expression for dynamical friction that dates back to Chandrasekhar. But we have seen that this is a fairly good description of what happens in realistic galaxies. And in fact, we validated our semi-analytical approach against full M-body simulation, also in disk-like galaxies that are supported by rotation. For example, here you can observe one of these evolutions, in which we have the time evolution of the radial separation, the angular momentum over the vertical direction over its initial value, and the related inclination with respect to the XY plane as a function of time. And as you can see, the semi-analytical evolution, the blue line, closely match the full M-body simulation, of course, considering a galaxy with the same initial parameter in the semi-analytical model. So we can get a very good description of dynamical friction in this stage. And so this means that we can capture the relevant physics driving this process. But of course, we can do much more than that. So this was a disk-like galaxies, but we also know that galaxies can be much more complicated. For example, in this work led by Elisa Bortolas, and in which I collaborated, we analyzed the PONOS zoom-in cosmological simulation. So we selected a Milky Way-like progenitor at very high redshift, 6 point something. And due to the messy cosmological environment, these galaxies develop a strong bar, so a strong non-axis symmetry within the disk. And what we found here is that stochasticity, further than dynamical friction, becomes a relevant actor in determining which is the physics driving the massive black hole in spiral. And in fact, a black hole can undergo either a rapid sinking or an erratic dynamic because the interaction with the bar is stochastic. Here, of course, since the computational cost is very high, we cannot run a lot of cases in order to study all possible parameter configurations. And so again, we decided to go through the semi-analytical path. We decided to model a Milky Way-like galaxies with these components, so a bulge, a disk, an halo, and a bar. It is described with this very simple potential here, but it is just to make the point. And so taking advantage of our semi-analytical approach, we decided to run several simulations in order to explore all possible parameter space of the initial orbital configurations. And we confirmed that the stochastic interaction between the bar and the unfolded black hole can actually affect the evolution. And specifically, since dynamical friction is extremely dependent of the mass of the perturber. When you have light massive black holes, the dynamical friction in spiral can be very long. On the other hand, but the torque exerted by a bar does not depend on the mass of the perturber. And so for very low mass system, we can have in spirals that actually proceed faster than predicted by dynamical friction timescale only. And so we have more mergers. We are more successful in spiral, especially at low mass. I can just give some glimpse of the dynamics in this kind of complicated system. So here we have a disk-like galaxy with a strong non-axis symmetry, and the bar rotates. So the potential is time dependent. And this is quite difficult to tackle. However, if you consider a reference system that is co-rotating with the bar, then the potential becomes static again, and you have a sort of a conserved energy that is, in this situation, is called usually the Jacobi energy. And this is the shape of the potential. You have 4 unstable equilibrium points, 2 maxima and 2 saddle points. And depending on the level of the Jacobi energy, you can have that a test particle can explore different region of the space. For example, if your energy is above the level of the maxima, then the particle can explore the wall space here. However, when the energy drops below the level of the maxima, then some region of the space cannot be accessible by the particle. And in particular, if this energy drops below the level of the saddle point here, then your particle, if it's outside, it cannot reach the central region of the galaxy. So the interaction with the bar prevents this particle to reach the central region. So for example, in the first column of this plot, in which you have the XY projection of the orbit in the co-rotating frame, and then the evolution of the Jacobi energy and the evolution of the radius. The color code is the time that is passing. You can see that in the first plot above, the Jacobi energy drops just below the value of the energy at the saddle point that are over there. And in this situation, since the massive black hole is starting outside the co-rotational radius, it cannot get inside because the torque of the bar is too strong and dynamical friction cannot help the massive black hole to reach the central region. But since the interaction is stochastic, you can have the very opposite situation. So for example, in this case here, at the first orbit, the massive black hole interacts strongly with the bar, pass through the saddle point here, and can reach the central region without any problems. And dynamical friction here is very efficient in bringing the massive black hole to the center. And then, of course, you can have situations that stay in the middle. So the take-home message from all these studies is that, yes, dynamical friction is a very important phenomenon in predicting which is the large-scale evolution of a massive black hole, or in general, a massive perturber inside the galaxy. But also, since galaxies are complicated system, we have to consider that the stochasticity is one of main actor in shaping the larger scale evolution. So if everything goes well, then massive black hole can reach the central region. And then they can form what is properly a bound binary, a bound Keplerian binary. From this now on, dynamical friction and the larger scale processes now are quite inefficient in influencing the evolution of binaries, but other processes can further shrink these binaries. For example, one of these is the stellar-driven hardening. So the interaction of the binary with single passing star close to the binary. So we have a binary in the center of a galaxy. A star can cross the orbit of the binary. And during this complex three-body interaction, generally the final outcome is the ejection of the star because of the huge mass difference. This process brings away tiny fraction of energy and angular momentum from the binary. So this process, repeated billions of times, actually shrink the binary. And it has been demonstrated that this process can be described by this very easy equation here that describe the evolution of the semi-major axis and the eccentricity, and that can be linked to the properties of the environment. Rho and sigma are the density and velocity dispersion at the influence radius of the binary. However, as I said, stars are ejected during this process. So at some point, you have no more star that can interact with the binary. And so the reservoir of this star should be refilled in some way. And this gave rise to the infamous last parsec problem. In fact, if you consider only spherical symmetric system, the only way in which you can repopulate this reservoir is through two-body relaxation that for galaxies can be longer than double time. However, it has been shown that if you consider non-spherical symmetric system as galaxies are, because they are not simple balls of stars, there are some centrophilic orbits that cross the center of the galaxy. And so the potential itself provide new stars to the binary that lies in the center. Because otherwise you don't have stars that you don't have no more star that can shrink the binary. So if the interaction rate between your massive black hole binary with stars is too low, the time scale blows up. Yeah, exactly. And in fact, here you have also, if you start with spherically symmetric galaxies and you merge them, at the end you form something that is not spherical, but is triaxial. And then you have all these kind of peculiar orbits that can cross the center of the merger remnant. And so new stars can reach the central region of the galaxy, and the hardening, the stellar hardening can go on. Of course, so since the last parsec problem now seems to be solved, we have to find out other, let's say, we have to answer other questions concerning the properties of the massive black hole binaries. For example, which is the eccentricity at the formation of the binary? Eccentricity is very important for what concerns gravitational wave emission. And so it is quite important to understand which is the possible eccentricity at formation. That is completely not clear. The process of stellar hardening is known to increase the orbital eccentricity, but if you start with circular binary, maybe is not enough. And so this is something that we are currently investigating in Milano Bicocca, and also other effects in the gas poor environment. For example, the massive black hole center of mass wandering that can be triggered due to galactic rotation. That is something that is not completely explored in the literature. And in fact, galactic rotation, it seems that can displace the center of mass of the massive black hole binary. And then if the binary moves around, the effective loss cone of the binary can become bigger, and so you can speed up the stellar hardening. So this was the gas poor environment evolution, but of course we know that in galaxies we have a lot of gas. And in fact, this is essentially the only way in which we can observe very distant massive black hole. When gas accretes on a massive black hole, it can shine, and then you can observe it. Otherwise, you cannot. So we know that there is gas in galaxies. And yet the situation becomes a bit more complicated because we need full hydrodynamical simulation. So we need to numerically solve the Euler equation coupled with gravity. And this is not a straightforward task. Here, for example, you have a snapshot of a simulation in which you have a binary embedded in a circumbinary disk. Here there is also self-gravity, so the gravity of the gas matters here. So you can see that you can develop a strong spiral structure, and they can interact in a not straightforward way with the binary. And so yet there is no general consensus on which is the impact on the binary properties due to this kind of interaction between massive black hole binaries and gas. 10 years ago, probably one would have guessed that the interaction with the gas at the end can shrink binaries. But very recently, or quite recently, not so very, there were some works pointing out the fact that the interaction of a massive black hole binaries with gas can actually expand binaries. And so if you have binaries that are expanding, then there is a problem because at the end, you cannot reach the final phase of the evolution gravitational waves are emitted. And so this could be a problem for the forecasts for the gravitational wave experiment. However, we have to say that not all configuration can give rise to a possible expansion. And in some situation, you can still have the shrinking. But more than that, we decided in collaboration with Elisa, Alessia, and Alberto, that in Milano Bicocca, we decided to assume the worst case scenario and actually consider what could happen if binaries actually expand because of the gas interaction. But of course, since massive black holes live inside galaxy, we have to consider also the competition with the other evolutionary process, in particular the stellar hardening, as I already mentioned, and also the small scale evolution due to gravitational wave emission. And specifically, we consider that the interaction with the gas change the semi-major axis according to this very simple relation here, in which the accretion rate seems to be quite crucial. We also assume that this regime is valid as soon as the disk is non-self-gravitating. So the mass of the disk is negligible with respect to the mass of the binary, because all these expanding results were found in this very specific regime. And this is in fact the expression for the self-gravitating radius, that for a 10 to the 6 solar mass binary is around 10 to the minus 2 parsecs. So in our scenario, we assume that the expansion stops when the semi-major axis of the binary reach the self-gravitating radius. So here we have the processes that we are plugging in. Of course, we are doing a very simple semi-analytical work in which we just numerically solved the equation of the differential equation that describe the time evolution of the semi-major axis due to these three processes here. So we have the stellar hardening that shrinks binary. We have gravitational waves that shrink binaries. And then we have the gas interaction that expand binaries according to this recipe from Munoz and collaborators. And what we have found is that we can have actually expanding binaries, but this binary have to accrete a lot. So the Eddington fraction of this accreting binary has to be close to 1. For example, if you focus on this plot, the top left one, in which you have the evolution of the semi-major axis as a function of time, you can see that when the accretion rate is not very high, you have sort of a turnover, but at the end, you always shrink binaries. However, if you increase the accretion rate up to the Eddington accretion rate, then you can see that you have an expansion phase of your binary. So the semi-major axis enlarges. But as soon as it meets the value of the self-gravitating radius, then the expansion is stopped because for our assumptions. And the important point to get is if you accrete a lot, the mass of the binary will increase a lot. And so the gravitational waves becomes very efficient. And so at this point, we can see that regardless of any expansion phase, we obtain the merger of the binary within a few hundreds mega-year. So this problem seems not to be a real problem for gravitational wave experiment. Irrespective of the evolution of in a stellar, in gas poor or gas-rich environment, if you have binaries that live for a long time, then the universe does not stop. In fact, we can have other galaxy mergers. And in this situation, then we can form triplets or even multiplets of massive black hole within the same galaxy. And this generally triggers a complex and rich dynamics that can again lead to possible massive black hole coalescences. This was the topic that I investigated during my PhD. So I consider again a semi-analytical approach in which I embed the post-Newtonian three-body equation of motion in some galactic potentials. And I also consider the effect of the environment, so dynamical friction and the stellar hardening. When I talk about post-Newtonian equation of motion, I'm talking about this. So these are the Hamiltonian for each order. And you can see that as soon as you go up the order, the situation can be quite complicated. And then you have to derive the equation of motion from this. But this is another story. I can give you a sketch of the possible evolution when you have a three-body system. So in this plot here, you can observe the time evolution of the relative separation between each pair of the involved bodies. So the blue line is the relative separation between body 1 and body 2, the red color between body 1 and body 3, and the green, the same for body 2 and body 3. So at the beginning of the evolution, you have a binary at the center of the galaxy here. And then you have an intruder that starts from kiloparsec scale. Then, because of dynamical friction, this intruder gets closer and closer. And at some point here, you form what is called an hierarchical triplet. So an hierarchical triplet is formed by two very separate binaries, a closed inner binary, that is the original one in the center, and an outer binary formed by the center of mass of the inner binary and the intruder. In this specific configuration of hierarchical triplet, if the relative inclination of the orbital plane of these two binaries is sufficiently high, above a certain threshold, then there exists a specific mechanism, the Kozyliov mechanism, through which you can exchange angular momentum between the two binaries. And these exchanges generate oscillation of the relative inclination and the eccentricity of the inner binary. By lowering the relative inclination, then you can increase a lot the eccentricity of the inner binary. So this is what happens here. The spread of the relative separation means that the eccentricity is growing a lot. And the process is very efficient when the initial relative inclination is close to 90 degrees. So you have orbits that are essentially polar. In this situation, the eccentricity can grow to very large values. And as the third black hole gets closer and closer because of the stellar hardening, you can excite a very high eccentricity that at some point drops below here. And the binary merge because we are using post-Newtonian equation of motion with encoded the emission of gravitational waves. So here we have a merger of a massive black hole binary. We can have situations that are completely opposite. So the relative inclination is not high enough. Here is around 20 degrees. So we have a very boring evolution for the hierarchical phase of the triplet. But at some point, since the final fate of this evolution is the dynamical instability, because the third body gets closer and closer to the inner binary, when you have three massive black holes, more or less of the same mass close together, the system is very unstable, and then we have a switch from a secular dynamic to a strong chaotic dynamics in which we have ejection, exchanges, and so on. And in fact, here we have an exchange. The change of color means that the new inner binary is formed by body 1 and body 3. But this is not the end of the story, since the ejected body can still perturb the inner binary until at some point, here in the corner, the last strong interaction can excite a very high eccentricity in the inner binary, and again, gravitational waves can take over and the binary can merge. Of course, these are few examples. To actually infer which is the probability of this interaction, we decided to run several simulations, around 15,000. And you can see that, again, the process works like that. You have binaries that are at low frequency, so large semi-major axis, at almost circular. Here is the logarithm of the circularity. So here means circular binary, here very eccentric. As the interaction starts, you can pump up the eccentricity up to very high values because of the Kozyliov oscillations or chaotic interactions. And then at some point, gravitational waves can take over because gravitational wave emission becomes extremely more efficient when the binary is eccentric because it depends on the pericenter passage. If the two black holes pass very close, they emit a lot of radiation. So here, gravitational waves take over and they follow the track close to the merger. And what we have found is that a non-negligible fraction of binary, around 20–30%, can actually undergo a merger event because of this mechanism. And of course, the main driver is the high eccentricity. So since I talk a lot about gravitational waves, then we can reach the final phase of this long evolution. So when gravitational waves dominate the dynamics, and the binary shrink because of this emission. So all the processes that have been highlighted in this long journey participate to this very last phase. So the theoretical modeling is instrumental in order to assess which can be the merger rate of this kind of binaries. And in order to provide reliable detection prospects for the gravitational wave experiment, it is very important to model at our best all the previous evolution. And in fact, gravitational wave experiment need a lot of input from theoretical modeling. And in particular, we need large population sample that can say which kind of sources we can observe. And for example, this is something that we have done in the past. So here we have the standard dilemma of accuracy versus efficiency. So we can use cosmological simulation, but they are very expensive to run. Then we can use semi-analytical model of galaxy formation and evolution. So these are very simplified approach to mimic the cosmological evolution. They are based on what's called the Presen-Schechter formalism. So you can simulate a cosmological merger tree at different redshift. And then you can use a simplified recipe to mimic the baryonic physics and the black hole formation within this formalism. And of course, they are tuned on more accurate results, but of course, we have to rely on several approximations. And black hole evolution within galaxies can be implemented through the introduction of some time delays. So cosmic time passes, you have halos of dark matter that merge. So galaxies within them merge. When two galaxies merge, then you can start your clock and say, okay, based on the condition of these galaxies, we can have different processes that can drive binaries towards coalescence. And then you introduce a delay. So after that time delay, the binary will merge because of one of the possible processes. Here we assume that binaries can merge according to these three processes. So the stellar-driven hardening, the gas-driven hardening, or because the interaction in a massive black hole triplet. We consider then two very opposite scenarios. So a more standard one that we name model delayed, remembering these time delays, in which all binaries can merge according to all these three possible channels, depending on the specific condition of the simulated galaxy within the code. On a much more pessimistic approach, called model stalled, we assume that binaries cannot merge alone, but they always need to interact with another massive black hole. For both of them, we also consider two different seeding prescriptions. So the process that can provide seeds, the massive black hole seeds that are essentially light seed forming from the first population of the remnant of first population of stars, and heavy seeds that are seeds that are usually much more massive. They can form from some more exotic phenomena like direct collapse, and they can be much more massive, around 10 to the 4 or 10 to the 5 solar masses. So at the end of the day, we have 4 realizations of our universe, and we can use them to say something about the detection prospects of the forthcoming experiment. I can start with the pulsar timing array. So pulsar timing is a very smart idea to detect gravitational waves and exploit millisecond pulsars that are located in our galaxy. The process, the experiment will be sensitive to what is called the gravitational wave background of massive black hole binaries. So the incoherent superposition of all the gravitational wave signal emitted by all binaries across the universe. And of course, it will be sensitive to the more massive ones in the range from 10 to the 7 up to 10 to the 10 solar masses. So the goal of the experiment is to monitor several millisecond pulsars in the galaxies that are up to date the most stable macroscopic clocks that we have. So the experiment works like this. So you go to the radio telescope, you measure the time of arrival of the pulses that arrive on Earth. And at the same time, you have to compute a timing model of your pulsar. So you have to construct a model that describes the physics driving the emission on the pulsar, how the radiation propagates toward the Earth, and the motion of the Earth itself within the solar system. That is not an easy task. So you have your observation, you have the timing model that predicts the time of arrival of the pulses, then you compute residuals. Then, if you have the residuals that are growing with time, this means that there is some unmodeled effect. And one of the unmodeled effects is the passage of gravitational waves, because gravitational waves squeeze the proper distance between us and the pulsar that we are observing, and this changes the time of arrival of pulses. Of course, the deviation are around the nanoseconds, so the experiment has to be very precise. But the trick that can tell us that we are quite sure we can detect gravitational waves is that we have to look for a specific correlation pattern among the residuals of all the observed pulsars. Because of course, if you rely only one single pulsar, then your model can be not accurate enough to describe the emission, and so you cannot trust it. But if you cross-correlate among all your array of pulsars, then you can increase a lot the precision of your experiment. And so this is the correlation that you have to look for in the data. So between two pulsars separated by this angular separation, if the correlation goes like that, a links and down correlation, then you are quite sure that you have detected gravitational waves. But since we have our synthetic universe, we can already say which is the level of the background that we have to expect from our assumptions. So here in this plot, you can observe the characteristic strain of the background as a function of the observed frequency. And so there is essentially no dependence on the seeding prescription because, as I said, the gravitational wave background that is detectable by PTA is dominated by the most massive binaries. And so there is any information about the seeding prescription has been washed out. But there is a difference between model delayed and model stalled. So the standard scenario and the pessimistic scenario. So in the pessimistic scenario, you would expect that the background can be much lower because you have less binaries that can merge. But this is actually not the case. So I will focus your attention on this orangish line that is the background for model delayed, and this light blue that is the background for model stalled. As you can see, the normalization of the two backgrounds is not dramatically different, but only a factor of 2 or 3. So even if binaries cannot merge alone in binaries, in galaxies, the hierarchical growth of the cosmic structure provides new galaxy merger. And if you form triplets, then at some point you can merge some binaries. And these binaries that can merge can keep the merger rate sufficiently high in order to provide a quite important background that is not dramatically suppressed. Still, the sensitivity of the experiment, that the sensitivity curve here, is not enough to reach this level. But in the forthcoming year, we expect that the sensitivity will lower down in this direction. So here. And so at some point, we can tell which is the true realization that we can have in our universe. Okay. You're right. And of course, these are exciting times for PTA experiment because very recently, the Nanograph collaboration, so the North American pulsar timing collaboration, has recently published a paper claiming that they have detected a common red noise in their data. The key point is common versus correlated, that are not the same. And if you want to detect gravitational waves, you need the correlation. But still, the analysis is going on. This is quite promising. And so stay tuned because in the next couple of years, we could have a detection of gravitational waves from this kind of experiment. And this can tell, the level of the background can tell a lot about the population that of massive black hole that we have to expect in our universe. Okay, so I can finally jump towards LISA. So LISA will be a very ambitious mission. So will be an interferometer in space made of a constellation of 3 satellites, and will be a big interferometer with 1 million arm length. So quite complicated to construct, and hopefully will be in place around mid-30s, so in 12, 15 years or so. Differently from PTA, LISA will be sensitive to the very opposite mass range of massive black hole binaries. So from 10 to the 4 up to 10 to the 7 solar masses. And you will be detect single coalescing sources. So for example, this is the sensitivity curve of LISA that peaks around, LISA is most sensitive around millihertz frequencies rather than PTA that is sensitive to 10 to the -8 hertz. And these tracks here are merging massive black hole binaries. And you can see that in LISA, you can observe them maybe months or years before the coalescence. So there is a lot of information encoded in the waveform of these mergers. And so a lot of our theoretical study is in the direction of telling which can be the properties of the binaries that reach the coalescence in order to inform people that are constructing the waveforms, in order to tell them how this waveform should be. They have to consider very high eccentricity. They have to consider very highly spinning or massive black hole binaries. And additionally, an interesting synergy will be with electromagnetic observatories, because with the gravitational wave parameter estimation, you can point which is the region of the sky in which you have to expect these binaries. And so you can do multi-messenger astrophysics. That's all. Again, considering our synthetic modelization of the universe, we can say something about which is the expected merger rate for LISA. Here, the information about the seeding procedure is much more relevant than PTA. And so, for example, in this plot, you can observe that different seeding prescription can give so in this plot, you can observe the merger rate as a function of chirp mass and redshift, color-coded. And overplotted, you have the SNR contours of LISA, so the famous waterfall plot. So this means that when the SNR is around 3000, you can resolve very well your binary. When you are here, the signal to noise is 8, that is generally considered the detection threshold. So yeah, you don't have to expect very good data here. But anyway, along the column, you have the model delay with different seeding prescription, and you have model stalled according to the different seeding prescription. So comparing model delay and model stall, you can see that the shape is more or less the same, but of course there are less events that can be observed. Instead, changing the seeding prescription, you can see that the shape of the merger rate changes a lot. So in fact, here you have a lot of mergers that are concentrated at very small mass for a massive black hole, of course, and around redshift between 10 and 15, that is quite high. Instead, for the heavy seed prescription, we have much of the merger concentrated in the sweet spot of LISA, and at the peak is at a lower redshift. So if you detect in LISA several mergers that are pointing in this direction, then you can say that most part of the seeds could be light, and you don't have to need to think about exotic formation mechanism for heavy seeds also. These are the numbers that we have, and even in model stalled, that is the pessimistic situation, we have tens of merger in the Fourier merger. So we are quite happy about that. And moreover, in model delayed with the heavy seed prescription, 1/3 of all coalescences that can be observed by LISA, of course, are from the three-body evolution channel, so the interaction within a triple. And this brings interesting consequences, because as I said, these binaries, if they merge because of the interaction with another massive black hole, they generally have a very high eccentricity at a certain point during the evolution. And some of these eccentricity can be retained until the very last phase of the evolution, so when they enter the LISA band. So if you detect binaries in the LISA band that are very eccentric, then at some point, you can say that, okay, this binary have followed a very strong dynamical path. And so this could be another way in which you can constrain the possible evolution of the massive black holes. And I still have time. Okay. Last but not the least, as I was said, there could be very interesting possibilities for synergies with electromagnetic observatories, like, for example, LSST and Athena. In fact, as I was saying, gravitational wave detectors can, LISA specifically, can tell you where you have to look for your gravitational wave sources. Of course, if the source is very far away, then you have thousands of galaxies within the field of view of the experiment. But as you can see from this plot, this is the error on the sky localization, for example. As soon as the binary is proceeding towards coalescence, then you can shrink your field of view. And at some point, you can meet the field of view of some of the experiments, of the observatories, like, for example, SST, the dashed dot line, or even Athena, very close to the merger. So in some situation, you could be able to do multi-messenger astrophysics, because you know exactly the gravitational wave signal, and you know more or less where you have to point your experiment. Unfortunately, we don't have a very elaborated idea of how a massive electromagnetic counterpart of a massive black hole merger could be. So we need still to work about this, but there are several theoretical studies about that. And of course, since we are modeling the very last phase of the evolution, we need the numerical relativity. But again, the theoretical studies about the massive black hole binary path to coalescence can provide sensible initial conditions for this kind of complicated simulations. And so at some point, you can figure out what we have to expect in the sky in the following years. And so I can jump directly to my conclusions. So the massive black hole path to coalescence is not always an obvious outcome of galaxy merger. We have several processes that can drive this long evolution. And it is not always straightforward that binaries can merge, but some of them can. We are quite sure about that. A meaningful assessment of the massive black hole evolution in timescale needs an extensive parameter space exploration. It is very good to understand the physics, but we also need statistics. So we have to collect a lot of information. And so we need tools that can allow to do that, can allow us to do that. And if you analyze the gravitational wave waveform, we can extract a lot of information of the previous evolution. So we need very precise waveform template. And finally, the synergy between gravitational waves and electromagnetic observatories will be crucial to get the highest scientific reward achievable by upcoming missions. So thanks for your attention.